Hello everyone. Welcome to Mega's monthly webinar series. Today's topic is Advanced End-to-End Testing. In this session, we'll be discussing why the industry is shifting away from discrete testing of protection functions towards a more comprehensive end-to-end testing technique. My name is Yurto. I'm the Marketing Communications Engineer for Mega North America, and I'll be acting as the moderator for today's presentation. I will be supporting you on any technical issues or questions for our presenter during the session. On the right side of the screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segments. You will receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and I will interject them as we have time. Our presenter today is Abel Gonzalez, Mega's Applications Engineer. Abel is based out of our Mega office in Toronto, Canada. Thank you for joining us, Abel.
Okay, let's go. Well, all right. Thanks here for the presentation. We are going to be talking today about end-to-end testing. And, well, why end-to-end testing and what is it all about? Let's talk about the following diagram that we have here. It's a line differential relay diagram. We have a line, we have a couple of relays, one on each end of the line, which have to act together to protect the line in a differential scheme. For that, they need to talk to each other. And for that, they need to see the magnitudes on both ends of the line in order to determine whether the fault is inside of the line or outside of the protection zone. Now, the only way to ensure that you are testing such a scheme is to have signals applied to both relays at the same time in order to simulate either a fault inside the protection zone of both relays or a fault outside of the protection zone of such relays, and determine whether the relays are operating properly or not. At some point, someone might think, okay, I will apply the signal to the what I call here the local relay and see if it picks up. Then I will apply a signal on the other end to the remote relay and see if it picks up, and then I'm happy. But there are so many issues that could happen with the communication between the relays and with the interpretation of the signals that is made from and at both ends for the same fault that is applied on the line, that of course the only way to ensure the proper testing of such a scheme is to apply signals at the same time on the relays, and of course evaluate whether both those relays acted properly or not. So this is a definition that I came up with about what is end-to-end testing. You will find as many definitions as people approach in the field, but everybody agrees in the fact that end-to-end testing is a way to evaluate the entire protection scheme by simulating the effects of faults on both ends of the line, which have to be played simultaneously. And everybody also agrees that in order to do end-to-end testing properly, the ability to synchronize the application of injection of the signals on both ends of the lines is of the utmost importance. Now, why do you do end-to-end testing? Well, we already talked about it, but it's the only way to perform the simultaneous verification of the operation of all the elements of a protection system. There is no other way to verify the actual operation. Well, barring a fault happening on the system, an actual fault happening on the system when the system is in operation. And okay, if that happens and we haven't properly tested the system beforehand, then we are okay, fingers crossed, let's see what if the system operates. It's the only way available right now to engineers to verify the operation of the protection system as a whole. What do you test? Well, from the scheme that we saw before, it is clear that when you're talking about end-to-end testing, what you are testing is any protection scheme that includes remote communication between relays. This is an example. You have a line, you have a relay in side A, a relay in side B. They're talking using some sort of communications protocol. Relay A is communicating to relay B whether he thinks that he should trip or not. Relay B is relaying that same communication to relay A. If both determine that they have to trip, okay, then they'll trip together. What type of protections are tested using end-to-end testing? Well, line differentials, any communication-based distance protection, transfer trip schemes like permissive over reach transfer trip, permissive on the reach transfer trip, etc. So some sort of phase comparison schemes, some automation systems that work in either transmission lines, even in distribution places, where you have remote communications between relays that have to, shift the load or switch from one feeder to the other. Those are also schemes that are prone to be tested using end-to-end testing. Again, if we see the line differential relay scheme that we see here, we see that this one only has two relays, one on each end. This is a single and simple, I would say, application of end-to-end testing where you only have two ends. Since most applications are like this, and most applications of end-to-end testing are like this, we tend to think of end-to-end testing in two dimensions. We tend to think in only two relays talking to each other, and we tend to then think of end-to-end testing as, okay, we're just synchronizing two test sets and doing what's appropriate to test such schemes. But sometimes reality is that the system is not that simple. That's why you cannot define end-to-end testing in terms of just two systems or synchronizing just two systems. Sometimes you need 2, 3, or more systems operating simultaneously. And when I say systems, I'm talking about test sets or even test systems in order to, verify the proper operation of the protection schemes. Now, when do you do end-to-end testing? Well, most of the times when you're doing commissioning, also when you're doing maintenance. Okay, I mean, in commissioning, it's a no-brainer. When you're putting something into service, you have to test it all the way. You have to be sure that it's working properly, that it's no problem. Otherwise, you don't just put it into service. However, when you're doing maintenance, end-to-end testing is becoming more and more popular in order to verify that whatever happened during commissioning is okay, and that whatever changes happened in the system haven't affected the ability of the protection scheme to properly protect the lines or whatever. When you're doing troubleshooting, let's say you have a trip on a relay in a line, or you don't have a trip in a relay in a line, and you want to know whether the relay tripped correctly, or whether why didn't the relay operate. In those cases, you also do end-to-end testing. When you're doing regression testing, well, that's something for someone who is not, maybe in the utility, someone who is I don't know, building or manufacturing relays and wants to verify that his relays operate properly in this or that protection scheme, well, then they'll do it. Any other cases, I'm open to suggestions. Now, the diagram that you see here is what you will end up with in 90% of the cases when you're doing end-to-end testing. In a previous presentation by Megger, by Stan Thompson a few months ago, he talked about the signals that are used to guarantee the synchronicity of the test sets, during end-to-end testing. Now, here you see that you have, in both ends of the line, and each end of the line, you have the same things. You need to have a relay test set. You need to have some form of time synchronization, and you need to have, of course, the relay that is under test, or the device that is under test, which could be a line differential relay, a distance relay, any kind of relay that's going to, be participating on the scheme. And of course, in addition to this, you need your test cases, you need the people. Keep in mind that when you're doing end-to-end testing, it's not the typical testing that you do in a relay, where it's the tester with the relay himself, everybody else doing something else in the substation. Nobody is minding whatever he's doing. No, in this case, you need to have active communication with the other side of the line or whatever you're testing, and you also need to have whoever developed the test cases that you're using. You need to have that guy on call in case something comes up with the. But again, if you are either new to end-to-end testing, or even if you are a seasoned engineer, if you've done it many times, this is what you will see in most of the cases when you're doing end-to-end testing. In some cases, the GPS receiver is integrated in the test set. In other cases, the GPS receiver is external to the test set. In other cases, you don't have to bring the GPS receiver with you, because the substation itself runs, a synchronization signal that's good enough so you can use it on both ends. But you have no way of not having a timing signal that is good for the synchronization of both test sets. If you can have a timing signal that is good for both test sets, and at the same time it's the same timing signal that is being used to synchronize, to guarantee the time signal of the relay, that's even better, because then you can actually see that what the tests that you're doing, and that you have events in both relays that happen when you're doing your testing, and you have a way of matching the operation of both relays using the timestamps of those event files. Now, this is just a list of the equipment required to do end-to-end testing. Of course, this is according to Megger, right? 2 relay test sets. We, of course, are going to say Smart 36, Smart 36, Smart 410, whichever test set. However, as you know, this could be any relay test set. 2 synchronous time sources. We, Megger, we provide the MGTR. We'll talk about it later. In this case, well, we have the line differential relay. It could be any relay that participates in the scheme. Optical fiber. Well, this is the, I would say, the best case scenario. It doesn't have to be optical fiber. It can be any kind of communication medium that you have that guarantees the proper communication between the relays on both sides of the line through computers. Now, this is unavoidable today. Everybody that is into testing needs to use a computer. Because you will end up with, the test cases. You need to record everything that's happening. You need to talk to the relays to either read the configuration or change it, and whatever. My take in all this is this last line here: carefully prepare the test cases beforehand. Don't improvise, and understand fully the system that you're going to test before you go into the substation to do your testing. If not, you're going to end up wasting and losing a lot of time. This is the typical test connections between the MGTR2 with the Smart 36. As you see here, we have a computer. The computer is used to connect to control the Smart 36. You can replace the Smart 36 with any test set that you have available, or that is of your preference. But the concept is the same. You usually need a computer to talk to the test set, a computer to talk to the relay, and a computer to configure your timing reference. You will somehow connect your timing reference to your test set in order to begin the test in both ends of the line at the same time. In general, when you're doing end-to-end testing, you need to create test cases for each of the ends. Why do I say create test cases for each of the ends? Well, that's simple. You cannot go with the same test case for one end and the same test case for the other, because even for the same fault is seen on both ends differently. Even when you have the fault at exactly 50% of the line and everything is beautiful and nice, which is only maybe 0.01% of the cases, the actual signals are seen differently from both ends of the line, from the relays on both ends of the line. So you have to create test cases for each of the ends. Include enough pre-fault cycles. This is something that sometimes affects, and people don't understand why, especially with microprocessor relays. I guess I'll talk about it a little bit later when you see the diagram, the oscillographies that I have to show. And also simulate faults in different places along the line. When I say include enough pre-fault cycles, I'm saying that don't do something like this. Don't begin your test and maybe one cycle later go with the fault. Why? Well, the reason for this is that microprocessors relays need some time to load the filters that are used, to interpret the analog signal and convert that analog signal into discrete form, and then to convert them into the quantities that the relays use to make their decisions. That's why I recommend that whenever you can, include enough pre-fault cycles in your testing. 5 cycles is usually more than enough to have all the filters in the relays filled, enough information for the relay to know that it is in a stable state, and then go to the faulty state. Now, simulate faults in different places along the lines.
Abel, I have a quick question.
Sure.
So why do we synchronize our test sets with a complicated satellite system instead of just using the electrical system, which is already synchronized?
How would you go about synchronizing using the electrical system? Okay, I'm sorry. I don't have feedback here. Okay, when we are saying synchronize, we are saying that the test should begin at the same time on both ends of the line. We have a test set here and another test set here. Okay? Now, this test set needs to begin the test at the same time at the test set on the other end of the line. The distance between both can be 500 meters, 2 kilometers, or 200 kilometers. Okay? Now, the only way to guarantee that the test begins at the same time on both ends of the line is to have a common time source, okay? And with that common time source, I can tell both test sets to begin testing at the same time, or to begin applying or injecting the signals that I designed as the signals that the relays on both ends of the lines should see for a particular fault, okay? And the only way I have to guarantee that both relays test sets are going to begin the test at the same time, which is going to be as close to a simulation as I can get to a real case fault, okay? Because when you have a real case fault, that fault will propagate to one end of the line and to the other end of the line at the speed of light, and it will reach one end of the line, I don't know, a few microseconds, the other end of the line, a few microseconds later, okay? But I have to account for that in my simulations. Now, the only way I have to guarantee that there is an actual measurable moment to begin the test is to have a common time source. Now, when you're talking about synchronization using the power system, when this power system talks about synchronization, what it says is that the frequency of the system is the same in all places of the system. but it doesn't mean that the power system has a common time source or anything of the kind that I can use to actually know when to begin the test at one end of the line or to begin the test at the other end of the line. This is what I'm saying. This is what I mean when I talk about synchronization. I don't know if that's enough as an answer or if I should talk a little bit more. Okay, yeah.
Yeah, I think we can move on. That's probably good.
Okay,
Thank you.
No, I just wanted to know if was satisfied or not. Okay, we can. If not, we can always go and have a longer discussion, a longer conversation about this a little bit later. Now, where was I? Okay, now simulate faults in different places along the lines. Okay, for the same reason that I said that even when you have a fault at 50% of the line, you need to actually create signals for relay A and relay B, and because relay B is going to see a fault here differently than the relay A. Well, you need to make sure that you are protecting the line properly, and that relay B and relay A are acting, together in a manner that allows for the protection of the line for different types of faults. I say here 10%, but you can simulate the fault as close as you want to relay A, a fault as close as you want to relay B. Usually, I recommend 10%, 30%, 50% of the line, 60%, 90%, which is in this case would be the opposite, is 10%, and of course faults outside of the protection zone to see what happens when relay B has to maybe act because it is falls into its zone 3 or 4 or whatever, but relay A doesn't have to, or maybe it has to because it has a. But the point is you have to be creative with the types of tests that you prepare, and don't just fall into, okay, let's do a fault at the 50% of the line, that's fine, and let's move on. Now, the main approaches to end-to-end testing are using what we call state playback, and the other one is using DFR playback. Okay. State playback. I'm gonna talk a little bit about state playback. What you do is you determine what are the voltages and the currents in both ends of the line for 3 different states. In one state, you will call it, I don't know, the pre-fault state, and you will mean by pre-fault a state in which you have steady state conditions, you don't have a fault, you have something going on in the system that could go on forever and nobody has to care about that. Okay? Now, the faulty state would be the moment when a fault hits the system, and then the post-fault is what happens after such fault, was cleared by the protection system. Okay. Now, if we go into, going with the philosophy that we talked about before about, using external and internal faults and whatnot, we can say that here, we have a pre-fault of, 3 amps, a fault 12 amps, and a post-fault of 3 amps. Since it is an external fault is something happening here outside of the protection zones of these 2 relays, which are acting in a 87L or line differential relay scheme. Since that is the case, well, we would be expecting these 2 relays not to operate and somebody else to clean the fault for them. Okay. And in this case, what you do is you put 3 amps in the pre-fault state, then 12 amps during the fault. You have that fault last for a few milliseconds, as many milliseconds as you believe the fault should last until the whatever protection system takes care of that has as the clearance time. And then the post fault, which is the return to normal conditions for the system. Now, how do you do it? Well, you use a state simulation tool that many relay test sets have available. Of course, I'm going to talk about the RTMS, of the relay test management software from Megger, which has a state simulation tool that can simulate up to 15 different states. For this one, we only need 4 states. Since we are doing end-to-end testing, we need to make sure that this pre-fault state begins when we want it to. Okay? So for that, we synchronize the system. We ask the system to wait for the IRIG-B signal, and during that time, the system, the test set will be applying nothing. It will just be there in idle state, waiting for the IRIG-B. And in this case, I programmed it to start the test at 13:45:00, which means that at 1 o'clock, at 1:45 p.m., the next state will begin. This state number 2, remember that we had 3 amps on the pre-fault. Okay, state number 2, we will have 3 amps. This will be a pre-fault. Now, I programmed here a timeout of 500 milliseconds. That's 30 cycles, which in my opinion is more than enough to, as pre-fault. In this table here, I have 5,000 milliseconds. That's equally good. I prefer to use shorter times. It makes my life easier. Since, like I said, 30 cycles is, in my opinion, more than enough for this kind of test. Well, let's go with it. State number 3 would be the fault. I will just wait for 48 milliseconds, which is roughly equivalent to, roughly, I think it's actually exact 3, no, it would be 50, a little bit more than the 48 milliseconds that we said before. But the point is, I'm going to wait for this time. Then I'm going to go into state number 4, which is going to last the same thing, 500 milliseconds. This is why we call it the states playback, because we have 3 definite states. In one, we have the pre-fault values, then we have the fault values, and then we have the post-fault values. Okay? In this case, since we are expecting the relays to do nothing, and we consider any trip during this condition a fault, then we have a couple of options here. We could have programmed one of the inputs in the test set to abort the test if we needed it, or we could just, play the test and go to the relays event files and see what happened there. We could, following the philosophy that we talked about before, first an external fault, then an internal fault, simulate an internal fault at 50% of the line, and for that we just create the appropriate states in the previous fault. Notice that for the remote relay, we said that the current in the faulty state was going to be 180 degrees apart. Okay? Which means current flowing behind the relay, to say it somehow. In this case, since it is an internal fault, and this relay is looking to the left, relay B is looking to the left, in the faulty state, that relay will have the current in phase with the current of the local relay. Not in phase, actually 180 degrees apart, but since this one is looking on the opposite way, well, it would be 0. My point is, just keep in mind that in order to create a fault, all you need to do in this case is to reverse the angle. Okay? Now, how do you do that? Well, you do it the same way. You create the same states that we created for the first case. We do the same. We create a fault and a pre-test status or state in which we'll be waiting, the test set will be waiting for the IRIG signal. In state number 2 will be the pre-fault state. Then on state number 3, we will have on state number 3, we will have the fault. Since we have the fault here, we have to make a couple of changes from the state number 3 that we had before. In this case, we are expecting the relay to trip. Since we are expecting the relay to trip, we are going to go on and program binary input number 2 in the test set to, listen to that output from the relay. And we're going to say that once it trips, it goes into the next state, which could be my post-fault state of 3 amps, or I could say 0 amps, depends on how do I, want to play the, in this case, I should have programmed 0 amps, not 3. Anyway, something that is the post-fault state that you consider that is a good condition operation. Since there was a trip in the breaker and there's nothing else, it should have been 0. I'm sorry about that. Now, what do you need to, consider in this case? You need to configure your timers. In this condition, this timer will begin in state number 3, which would be the moment when the fault is applied to the system, and the stop condition of the timer would be post number 2, which is the binary input that I'm using at the relay. Remember, I was using binary input number 2. The binary input that I'm using at the relay to, account for the tripping of the, not on the relay test set, to account for the tripping of the relay. After that, all you need is, get your results, and of course, get the test report. As an aside, a comment for everybody else. Testing is about ensuring the reliability of the system. For the guy who's doing the testing is about that, but also about the test report. So for him, it is very important to actually have the test report, and if he can have it automated, it's a lot better. Again, end-to-end testing. This is a picture that I want you guys, to go home. If I want you to go home with something, it's with the picture that what is end-to-end testing and how is end-to-end testing performed today. Okay? Now, we can also use a ComTrade playback utility, which allows us to do essentially the same thing that we did with the states playback, but there are many advantages to using ComTrade. For those who don't know what ComTrade is an IEEE standard. It stands for Common Transient Data Exchange. It's a standard that allows for, the representation, a common representation of oscillography coming from any kind of oscillographic recorder in the system. And since it is a standard, it allows people to see in standard tools that some of them are free in the internet. You can find them, or some are built into the configuration tools used to configure relays. And the other thing that it allows is not just to see, but to be played back using modern relay test sets. Since the ComTrade is standard, it also allows to have hardware independency in terms of testing. As long as your relay test set has the ability to play back those files, then you can use any relay test set in order to play back those files and, either play them because there was a fault in the system, the fault got recorded in a relay or in some sort of recorder, and then you can use it to play it back in the relay and see if it operated properly, if it didn't operate properly, why did it happen, or most, if not all, simulation tools used today to simulate power systems have the ability to generate ComTrade files, which is what makes it so attractive. Because on the other hand, in the ComTrade files, You can, since it stores the actual oscillography of whatever happens or is going to happen or is proposed to happen in the system, it can include the actual behavior of the power system, not just the fact that you have a steady state and another steady state, which we had with the states playback, and then another steady state, the pre-fold, fold, and then post-fold. In this case, we can actually include things like exponential decay when a fault comes up, harmonic distortion. You can even simulate CT saturation and stuff like that. That's why I prefer to use, whenever I have the possibility to use COMTRADE. Again, one of the problems that you find when you're using COMTRADE is that sometimes you get the fault oscillography, or the fault, the event of the fault, and there are not enough pre-fault cycles stored in that oscillography. The reason for that is, well, sometimes people do it to save memory, or in other times you do it in order to get as much information you can from the fault and not so much about the pre-fault, which in my opinion is a mistake. You know, the faults don't happen alone. But the thing is that, or in isolation, the thing is that it is very easy in a COMTRADE file to manipulate it in order to include more pre-fault cycles. You can do it using Excel. You can do it in a notepad. You can do it in many, many different ways. Sometimes it's as easy as just copying a block of data and changing the timestamps in a very standard manner. You can get a COMTRADE from a relay, like I'm doing here. Then you can play back the relay. If you see, and we are talking about the same oscillography and represented using different tools. Since the COMTRADE is a standard, all the oscillographies are represented in all the different tools. The representation of the oscillography is the same. Here I'm using GE's, the UR Enervista configuration tool. They have a very good COMTRADE tool. Here I'm using one from another relay manufacturer. Here I'm using the DFR waveform viewer from ABTS, which is another tool that Megger has that is used to test using our test equipment. With this tool, you can get the COMTRADE file and play it back in the. I'm not going to show the particulars of that because that, I would say, is more akin to those who want to, go deep or delve into the use of ABTS. For the purposes of end-to-end testing, what you need to know is that you have the ability to get a COMTRADE, then play it back either manually or synchronously using another tool that comes in the same, that is built into the same software from Megger. And this essentially allows you to do the same that we did with the states playback. We can play back the fault into the relays at both ends of the line, or as many ends of the lines as I have at the same time. Right now, I think I'm kind of short in terms of presentation, but I did it a bit faster. Well, let me talk about what Megger has in terms of equipment. To do this test, Megger has a very nice line of relay test sets. Now, why is it good for the end-to-end testing that we're talking about now? Because we have a built-in IRIC-B decoder in binary input number 1, which can be used with either an external GPS device or to decode the IRIC-B signal that is running in many substations. So it's, I would say, a very good tool. In terms of the equipment itself, I'm not going to go and praise beauties of the equipment and whatnot. And we also have, as a complement for that, we have a GPS timing reference, which is what most people who use the Smart 36 to do end-to-end testing and end up using, because they can get from this timing reference, they can get the RFB signal directly into the SMRT, and they can do the test that way. In terms of end-to-end testing, let me go back to, because I want to mention something. In terms of end-to-end testing, you don't always need, I'm focusing myself in the presentation on all the time I'm talking about using the GPS and then using the IRIC-B signal. That's not the only thing that you can do using a GPS receiver. GPS receivers also have a pulse output possibility, which will give you a pulse whenever a particular time is reached, which means that you can begin your test when that particular pulse is given by the GPS receiver. Okay, so that's another way of beginning the test, because some test sets do not have the ability to decode the IRIC-B signal natively, so they need something else to give them that pulse in order to begin the test. You can, with our equipment, either use the IRIC-B directly into the equipment, or you can use that pulse, which will account for the same thing. Instead of using the IRIC, then here, what you will do is, okay, you will use binary input number 1 to act on a voltage pulse. That would be the only difference. Here, I'm finished.
Okay, sounds good. Well, this has been a really short webinar, so at this time the webinar is officially concluded, but based on feedback we got from our webinar series in the last year, we're going to have an extended Q&A session for about another 30 minutes to make sure we got all the questions answered.
Okay.
If you have any questions right now, please submit them into the Q&A box. For those of you that are leaving, when you close the webinar window, a survey box should pop up on screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so that we can continue to improve future webinars. A copy of the presentation will be emailed to you in the next few days, and a recording of the session will be available on our website at megger.com/webinars in the next 2 weeks. This webinar landing page also contains the schedule for all upcoming webinars and the recordings of all previous webinars. So again, if you are looking for any